Hello, so today we will be doing homework 2, part D, and first we're going to be expressing the heat diffusion equation from C1 as an algebraic expression via Crank-Nicolson differencing. So if you will recall from the last part, we had an equation of T at section J of time n plus 1 minus T of J at our current time equals R and times T J plus 1 n plus 1 minus 2 T J n plus 1 plus T sub J minus 1 at time n plus 1. And so these are the temperatures at all of the future times. And then we also have the temperatures at our current times. So we have T at section J plus 1 at time n minus 2T J and then at time n, and then plus the temperature at section J minus 1 at time n. So this is the equation that we have, and these are all of our unknowns. These are the temperatures of the sections at the future time. So these are our unknowns, and these are knowns because these are at our current time. And so we can rearrange this a little bit and also recall that R equals alpha delta T over 2 delta X squared. And so we're going to rearrange this a little bit to expand it out and to also have all of our n plus 1 values on one side and then our knowns on the other side. So our n plus 1 values will be this, this, and then our n values will be these. So we can rewrite this to be T sub j at n plus 1 minus R T j plus 1 at n plus 1, and then plus 2R T sub j n plus 1, and then minus R T sub j minus 1 n plus 1. And so that is our left side of the equation, and then we'll put our knowns on the right side of the equation. So we will have T sub j at time n plus R Tj plus 1 n and minus 2R Tj n and then plus R Tj minus 1 n. And we can further simplify this by combining like terms. As you'll see, we have a common T sub j at n plus 1 here. And then over here we have a common T of j at n. So we can combine those terms and we will get 1 plus 2R T j n plus 1. Yes, and then minus R j plus 1 n plus 1 minus R j minus 1 and n plus 1. And we'll do the same thing on the other side. It'll be 1 minus 2R of T sub j at time n, and then plus R Tj plus 1 plus R Tj minus 1 time n. So this is our algebraic expression via the Crank-Nicolson method, and this is what we will use in our collab. So again, as we can see, These are our unknown terms, and these are our known terms. So this will be the equation that we will use later. So for part 2 of this homework, we will be using the von Neumann stability analysis to show that the Crank-Nicolson differencing method, the equation we came up with, will be stable no matter what value we use for r. So in part C, we can recall that we set t sub j at time n to be equal to e to the I k delta x times e to the negative alpha k squared delta t. And so we set t of j plus 1, the section to the right at time n, is equal to t sub j of n or multiplied by e to the power of I k delta x. And then similarly, we have defined t at the section to the left of j at time n to be equal to t sub j of n times e to the power of negative I k delta x. And so we can use these values here and plug them into our Crank-Nicolson method equation above. All right, so we will get 1 plus 2r t j of n plus 1, and then we will get minus r, and then this equation right here, we'll use this, t j n e to the I k delta x, and this will be n plus 1 because this is an n plus 1 term. And then minus r times t j n plus 1 e to the negative I k delta x because it is to the left now. We can do the other side as well. Be 1 minus 2r t sub j of n, and then plus r times t j n e to the I k delta x, and plus r t j n e to the negative I k delta x. And next we can simplify this further by combining our like terms. We can see that we have common terms on this side of t sub j n plus 1. And then on the other side, we have common terms of t sub j at time n. So we can rewrite this as t j at n plus 1 will equal 1 plus 2r minus r times e to the I k delta x minus r times e to the negative I k delta x and then on this side it will be t sub j of n 1 minus 2r plus r e to the I k delta x and then plus r e to the negative I k delta x. And next, we are just going to simplify this again by dividing everything by this TJN term and this term here. So we will get the temperature at position J at time n plus 1 over the temperature at position J at our current time will be equal to 1 minus 2r plus REIK delta x plus RE negative IK delta x over 1 plus 2r minus REIK delta x is RE to the negative IK delta X. And in part C, we used the trig identity e to the I plus e to the negative I of x each will equal to cosine of x. So we can use that in this equation, and we will get t sub j n plus 1 for t sub j of n to equal 1 minus 2r plus 2r cosine of k delta x over 1 plus 2r minus 2r cosine k delta x. And then we can simplify this again by factoring out 2r. And then minus 2r will be minus 2r of 1 plus cosine k delta x over 1 plus 2r of 1 minus cosine k delta x. All right, so now we will use the von Neumann stability analysis to look at this. So we know that with the von Neumann stability analysis, this term here, this ratio of temperatures at the current time versus the future time, it has to be less than 1 for stability. So we will look at this other side, we'll look at the absolute value of it, and we know that that also has to be less than 1. So let's look at just our term in the parentheses here. We know about the cosine function that its minimum and maximum values are -1 and 1. So if we plug in those values to what's in this parentheses, we will get 1 plus or minus 1 for its maximum value, or 1 plus or minus -1 for its minimum value. And so if we do 1 plus 1, you'll get 2. 1 minus 1 will be 0. 1 plus -1 would be 0. 1 minus -1 would be 2. So we can see here we will always be between the values of 0 and 2. So what's the term in these parentheses will always be a non-negative number. And it will always, so it will never be a negative number. So if we look at the rest of this equation, so 1 minus, and we will call this whole term here, because 2r will be multiplied by a non-negative term. So we'll call that a, and then in the bottom we'll call that also a. So for example, let's say a equals 0.5. 1 minus 0.5 is 0.5. 1 plus 0.5 is 1.5. So as you can see, this ratio here is less than 1. So this shows that by using our Crank-Nicolson method in our equation up here, we can use any value of r that we'd like, versus in the last problem, we were limited by just using an r value that was less than 0.5. So now we are going to be doing part 3 of this homework. We're going to simulate the time-dependent response of the same uniform bar that we did in the last video, but instead of raising it to 40 and 100 degrees Celsius, we are going to raise each end to 50 and 80 degrees. We're going to split the bar into 1 centimeter sections, and we're going to plot the temperature profile. So we know that we will have 50 sections, and we can go ahead and create an array to store our temperatures, we'll have its size n, and then each section will start out at 20 degrees. And we'll define the first value in that array as 50 degrees, and then the last value will be 80 degrees, and make sure we put a period there. And then we're also given an alpha value of 1 times 10 to the negative fourth. And our dt will be, I believe, yes, a time step of 0.1 seconds. 0.1 seconds. And then I'm also going to make that there. Then we're also going to have our dx to be, I believe it was 1 centimeter. Yes, 1 centimeter sections, and we want everything to be in meters, so it'll be 0.01 meters. And then we have to calculate our r, which will be alpha times dt divided by 2 times dx squared. And we can show our r value here. So our r value is 0.05, which is a lot smaller than the previous value that we used. But now we have to create an array, or not an array, a matrix. So we know our initial temperature on one side of the bar is 50 degrees, and on the other side of the bar, we're setting it to 80 degrees. So we have 48 different temperatures that we need to calculate. So we have 48 unknowns. So we need to create a matrix so that we can solve for these 48 unknowns. And so if we write out this matrix, we'll see we have diagonals of zeros, and we have diagonals of negative r, 1 plus 2r, and then negative r again. So we can define our matrix as AB, and it'll be numpy dot vstack. And then it'll be numpy dot full of n minus 2 negative r. And then numpy dot full n minus 2 1 plus 2 times r, and then numpy dot full of n minus 2 again, and then that negative r for those repeating diagonals. Right. And then we also need to define our x-axis. I will call that idx, and it will be numpy dot arrange number n. And then we need to plot, so we can do fig equals make underscore subplots. And then we can add our t equals 0, or our time equals 0 plot, so fig dot add scatter. And then we want our x to equal idx, or y to equal t, or mode to be lines, and then we want the name to equal t naught. We can show our fig. All right, so we have our one line of the initial starting point of the bar. We have one end at 50 and another at 80. And so now we can go ahead and plot the rest of our times here. So in order to do that, we will need to create a loop similar to our last homework part. So we will do for n in range, and then 10,000 according to the problem statement, I believe. Yeah, so 10,000 time steps. So that, and then we will define the other part of that array b, and will equal 1 minus 2 times r, times t from -1 to 1, and then plus r times t from 0 to 2, and then plus r times t from 2 forward. And we have to define this at 0, so it'd be plus, because we're adding, and we don't want to just override that initial value. And it'll be r times t at 0 as well. And then we'll define this last one, b of the last value is equal r times t negative 1. And then we want t from 1 to negative 1 be equal to psi pi dot solve rate. I'm going to do psi pi dot linear algebra dot solve banded b1, and then a, b, and b. And then we want to plot the results in 20 time step intervals. So we will do if n remainder 20 0, we will say fig dot add scatter x equals idx, y equals t, mode equals lines, and then our name will be equal to t equals n plus 1. Okay. All right. What I do here. Okay, so I did negative 1 to 1. It should be 1 to negative 1. All right, so this is looking like what it should. So we can see we have one side at 50 and one at 80. And if we look at T0, as we saw before, all of the rest of the bar is still at that 20 degrees Celsius. But if we look at T equals 1, it slowly will return, or not return, but it will slowly all go to a linear increase in temperature. So this is a very stable system that we have here. So for this final part, part 4, we're going to repeat what we just did, but with a time step of 10 seconds. So this time step will also change our R value, which we'll see. So our dt will change from 0.1 to 10 seconds. So as we can see, our R value will jump to 5, which is much larger of an R value than we've seen before. So we can see that obviously this looks a lot different than our steady state linear relation that we saw before. So we can actually look at t equals 0, everything looks normal, but then we go to t equals 1, and we see that there is an inaccuracy here because it seems our temperatures are jumping above our set points. But then we see as time goes on, it still will move towards that linear relationship. So even though we have this inaccuracy here, it still will reach stability, and we don't have any weird oscillations or anything. So this shows that the Crank-Nicolson method, we can still have stability with any R value of our choosing. So thank you for watching.